All right, we're going to go ahead and get started with characterizing our types of reactions. There are five main types that we're going to deal with today. And we want to start off by looking at our learning goal. Our learning goal today is to characterize the types of reactions. We want to look at what are the patterns that we're going to find. How will we know which reaction it is that we're dealing with? So let's go ahead and jump right into it. Our first example that we're going to use for these types of chemical reactions is synthesis reaction. Now, the characteristic that we'll use, and you can find this on your guided notes, the characteristic that we'll use for synthesis reaction is that there will only be one product. So an example that's given to us is looking at solid sodium reacting with chlorine gas. In the end, we form one compound, sodium chloride. In order to find this or to know that we're dealing with just a synthesis reaction, there's a base pattern that we're going to look for. We want to find A plus B yields AB. Looking at our example above, are we able to see this pattern? Yes, we have one element here, one solid part, plus another part, chlorine in its diatomic form, to form one solid compound. This is going to be our first and I believe simplest to deal with, because every single time we have just that little part that's remaining. We have one compound to look for. So this is our characteristic. Now, our second type of reaction that we're going to deal with is combustion. Now, I think everybody would love combustion reactions. Why? Combustion reactions are the ones where we get to set things on fire. And we're actually going to do a demonstration in class where you'll get a chance to see some things set on fire using this concept and using this type of reaction. Now, the example given to us here is the combustion of propane. Key pieces of information to look for in every single combustion reaction that we're going to deal with, combustion of a hydrocarbon, the latter half is going to be exactly the same. What do I mean? I'll have some hydrocarbon that's reacting with oxygen to produce carbon dioxide and water every single time. So I don't have to guess with anything on this one. It's all right there in front of me. Now, what about our pattern? This is our pattern that we're looking at here. CXHY, meaning that that X and Y can be any subscript, any number, plus an oxygen molecule is going to give me carbon dioxide and water. It's going to break it down into its simplest form. Now, characteristic goes back to pointing out those things that we just talked about. The fact that we have a hydrocarbon reacting with oxygen, and the products will be carbon dioxide and water. On your paper, you should be able to locate where we found those combustion reactions. For many of you who were going through and you realize that some of these equations are really, really long when you're balancing, those are usually your combustion reactions. So you have that in mind as you continue going on. Our next type of reaction will be decomposition. Now, this one is fairly simple because it's just the opposite of a synthesis reaction. Synthesis, we were putting together, building up. Now decomposition, we are breaking down or breaking apart. An everyday example of where we use this is hydrogen peroxide. When we get a cut or a scrape, many times we put hydrogen peroxide on it and it begins to bubble up. That gas, or those bubbles that are forming, is oxygen gas as it leaves your skin. What's left is just water, which helps to flush out the system. Our base pattern for our decomposition reaction will be AB yields, that's supposed to be an arrow, A plus B. So I start off with one compound, and then I break down into however many parts will come after that. Our main characteristic is that there will always, for a decomposition reaction, only be one reactant. This is something that we want to keep in mind and keep pushing for, so we can understand and see this one is definitely decomposition. Next, we have single replacement reactions. Now, just like you're thinking, replacement means I have to be switching something out. And because of that word single at the beginning, that means I'm only going to be switching or changing out one part. This is where a challenge comes in. because this is where we're going to see a slight difference in our base pattern. What do I mean? In our first base pattern, we have A plus BC yields AC plus B. This would be in a case where we have a metal as A. In that term, we're still dealing with an ionic compound, so we have to make sure that we have a metal and a nonmetal to make up this compound. Now, in our second form of this, we have A plus BC yields BA plus C. This is a situation where we have a nonmetal in at the beginning, and it can only transfer or replace the nonmetal. This is something that we want to be very, very careful with. A very easy way to remember this, though, is when we're dealing with our second pattern, we'll notice that usually A will be a diatomic. Now, we should by now remember our 7 diatomics. So, if you are still struggling with those, you want to take some time and make sure you remember them. They will come in very handy as we continue to go through this unit. Now, once we have finished this, our characteristic is one reactant that is an element or a diatomic with the other that is an ionic compound. Once we see this, whether it's the compound first and then the single element, or the element and then the compound, we automatically know this is a single replacement reaction. We need to look and see which of our two will actually be replaced. Now, the other thing that we have to pay attention to when it comes to single replacement reactions is what's called the activity series of metals. There are some metals that are very, very reactive, and there are other metals that are not as reactive. So we want to make sure we take the time to look at these, because it will only be able to replace, the metal will only be able to replace a metal that is lower than it on the scale. So as we're looking down these rows, you see how it decreases and it continues. I have to have a metal that is higher on the activity scale in order to be able to replace it within the reaction. If not, then no reaction occurs. We're actually going to see this in a lab activity that we're going to do very shortly. The same thing happens in terms of our halogens, or our nonmetals that we use in these cases. Fluorine being the highest in energy or having the most reactivity, iodine being the least. So these are things you want to keep in mind, and I will give you a copy of a chart and have it all around the room, so you'll be able to remember these without having to struggle with it too much. Now, our last and final equation that we're going to deal with here is called a double replacement reaction. Now, if single replacement reaction was we picked one of the parts of the compound and replaced it, double replacement means what we're going to do is we're going to switch both parts. Now, example given to us here, silver nitrate and sodium chloride react to produce sodium nitrate and silver chloride. The great thing that always comes from these, and even though it is not necessarily something that is set on fire or something that does this great huge explosion, we want to look at the fact with double replacement reactions, I'm usually going to get some kind of solid or a gas or something released so I can tell that a reaction actually did take place. Looking at our example here, you see that you have silver nitrate, the silver from the silver nitrate, and the chlorine from the sodium chloride come together to form a compound called silver chloride. This is insoluble, and remember we talked about this the other day when we talked about the properties in forming a precipitate. Insoluble means it does not dissolve. So, what is our base pattern? We have AB plus CD yields AD plus CB. The easiest way for me to remember, if you take your metals and move them directly over to the other side, as they are, then come back in the end and switch partners. So, B will now go at the end, and D will now go up front. But this is an easy pattern to memorize. Just remember, in the end, both are switching places. Characteristics: both reactants are going to be ionic compounds. In order to make this happen, we have to make sure that the compounds are ionic so that we can balance out the charges on the other side. Now, just as this is a little, I guess, summary for you to have in mind. Synthesis or combination reactions, two or more substances, one compound. Combustion, substance with oxygen, always going to produce water and carbon dioxide. Decomposition starts off as one compound, then moves to two or more elements or compounds. Single replacement and double replacement, looking to see which part, if not the entire ionic compound, will be changed around. So, if you have any questions, please write them down. Come back to see me so we can make sure that you are prepared for this as we continue to go on. Make sure that you keep up with the notes, and we will continue to break down each of these chemical reactions as we continue on through this unit. Have a great evening, and I'll talk to you tomorrow in class.